Well, let me know if you can see the screen. Is the screen visible? এবার ঠিক আছে? Okay. So in the last class, we have learned how to produce a parse tree with some production rule and semantic rules. So if you just use the production rule to generate some string, it is known as parse tree, right? But in that parse tree, if you include all the attributes of the semantic rules, it is known as annotated parse tree. Okay. In the last class, we have seen how to evaluate this expression using the annotated parse tree, right? But if you look at the annotated parse tree, you might not instantly figure out how we are getting this 19 here, right? Because we have done some uh, depth first search, then we have evaluated each value according to the semantic rules, and we have calculated the value 19, if you remember from the last class, right? So another thing is um, dependency graph, right? So what is a dependency graph? Dependency graphs are basically your annotated parse tree. Okay, so here are the bookish explanation given here. So in simple words, dependency graph is basically your annotated parse tree. Also, it has arrows indicating where the values are being calculated from. So in your annotated parse tree, you are calculating the attribute values, right? For example, you are calculating f dot val. So this val is a attribute of f, and you are calculating this value using this rule, right? So f dot val is equal to digit dot lex val. You are using this value to calculate f dot val, right? So dependency graph is nothing but annotated parse tree with the arrows showing from where the values are being calculated. Okay. Also, in your annotated parse tree, you have seen uh, these branches are written in solid lines, right? But in dependency graph, these branches will be dashed. Okay. So now we are ready to construct the dependency graph. We have dashed the lines, and we need to show where the values of the attributes are being calculated from. We are going to show this by using an arrow sign. So similarly, when we are evaluating SDD, we are first going to draw the dependency graph, and depending on that dependency graph, we are going to evaluate the values, right? So at the very uh, bottom, so if you do depth first search, so at the very first node is this node. Here it says digit dot lex value. So the lex value is 3, right? So the lex value is 3. So We have set this value as 3, and we're going to go up. So we're going to go up and we find this node, right? Now we are going to calculate the value of this node. So the value of this node will basically be coming from this value, right? Because we have a rule saying digit, if f produces digit, so the value of f will be the value of digit dot lexval. So the value of digit dot lexval is 3, and we're going to just convert the value of f val from this digit dot lexval. So we are taking the digit dot lex value into the f dot value. So we need to draw an arrow from digit dot lex value pointing to f dot value, right? And what is the value? The value is 3. So we're going to write 3 here. Okay. Now, if you traverse again, the next node is this node. So this node is basically T produces F. So this node, right? And the corresponding semantic rule associated with this uh, rule is T dot value is equal to F dot value. So we are going to get T dot value from F dot value. Okay. So we are going to get this value from F dot value. So again, we need to draw an arrow from F dot value to T dot value. Okay. So we're going to draw an arrow from here to here, and the value we are getting is 3. So now if we traverse, our next node is this node. We do not have any value associated with this node, right? If you look at the production, we do not have any semantic rules associated with this node. Now we're going to traverse again, and we're going to reach this node, right? So digit dot lex val, and the next value is, we got the star, the next value is 5. So the value of digit dot lex val will be 5. Okay. And after this node, our next node will be this node f dot val, right? So we need to calculate f dot val again. If you look at the production rules and semantic rules, if you look at the production rules and the semantic rules, we can see we can use the digit dot lex val to calculate the value for f using this rule. Okay. So we are now going to calculate the value of f dot val by using digit dot lex val. So we need to draw an arrow from digit dot lex val pointing towards f dot val. So the value will be 5. Okay. Now, where if you again traverse, our next node will be this node, right? T dot val. T dot val will be our next node. To calculate T dot val, we need to figure out from this rule. So here in the production rule, you can see to calculate T dot val, we need to use T1 into F. So this rule, T1 into F. And the semantic rule associated with this is T dot val is equal to T1 dot val into F dot val. So we are taking values from both this T dot val and F dot val to calculate the value of this T dot val, right? So we need to draw two arrows here. So we need to draw, no, multiplication sign is not being used. We're only using these two nodes T1 and F. Are we using this multiplication node? No, because this is a multiplication sign, not this node. Okay, so we're going to draw arrow from T1 dot val to T. Okay, and we're going to draw the value from F dot val to T. So we're taking these two values to calculate T dot val. What is the value of T dot val? 3 into 5, which is 50. Okay, now if you traverse again, the next node will be E dot val, right? Our next node will be E dot val. And if you look, the corresponding node is E produces T, and the corresponding semantic rules are E dot val is equal to T dot val. So you are getting the value from T dot val, right? So we need to draw an arrow here. So from T dot val, we are going to get E dot val, which is 50. Again, if you traverse, the next node is this, and it will go from here to here, and the next node is digit dot lex, right? So we have gotten the plus. Our next node is digit dot lex val, which has a corresponding value of 4. Okay, so here it put the value 4, and next our node is f dot val, right? If you traverse, our next node is f dot val. And now we need to put values for f dot val. And if you look here again, we're going to get the value from this production rule and this semantic rule. So f dot val is equal to digit dot lex val. So this digit dot lex val will basically be your value which is being set to f dot val. So the arrow will be from digit to lex val pointing towards f dot val, which is 4. So again, if you traverse, our next node will be T dot val, and the corresponding rule will be production rule number 5 and the semantic rule associated with it. So we are getting f dot value from T dot val. So we point an arrow here. Now, if you traverse again, you will go to this node, which is E dot val. So the corresponding node is from production rule 2, E produces E1 plus T. So this is your E1, this is your plus, and this is your T, right? So we are going to take the E1 dot val, and we are going to take T dot val to calculate E1 dot val. And how we're going to calculate? We're going to calculate using this semantic rule. So this is E dot val is equal to E1 dot val plus T dot val. So E1 dot val is 15 and T dot val is 4. So 15 plus 4 is 90, right? So again, if we traverse, we can see that our last node is this node, and after this node does not have any values or semantic rules associated with it. So our very last node is L dot val, right? So we need to calculate the value for L dot val. So for this, we can use the first production rule, which is L produces En, and the value of L is equal to value of E. So we are getting the value of L from E dot val. So we need to point an arrow from E to L. So this 19 is being copied here. Okay. So this is basically your dependency graph, right? So this is basically your dependency graph. So we have seen how we can transform your annotated parse tree into a dependency graph. So in your question, you might be asked to draw or evaluate SDD. If you are asked to evaluate something, you need to draw this dependency graph, and you need to show the proper arrows, right? So from where the value is being calculated, you need to point it with a proper arrow sign. Okay, wherever the value is being calculated, the pointer will point towards that value. So suppose f dot value is being calculated, so the pointer will point towards f dot value. Okay, so this is how you can draw a dependency graph and you can evaluate something. But if you are asked to just draw the annotated path tree, you will just draw the annotated path tree. And if you are asked to evaluate, then you are going to draw the dependency graph. Is it clear to everyone? Any questions on how to draw the dependency graph? No. Okay, so far we have seen two types of attributes, right? There were uh, two types of attribute. One is synthesized attribute and another is inherited attribute, right? So this is the type of attribute. Now we have two types of syntax directed definitions. So syntax directed definitions. What are syntax directed definitions? Syntax directed definitions are nothing but production rules and semantic rules, right? Here we have two types of SDD. So previously we have learned, so these are the attributes. So these are the attributes, these values are the attributes. The attributes are two types: semantic attributes and synthesized attributes and inherited attributes. Now we are going to learn SDD of two types. One is S attributed SDD, and another one is L attributed SDD. S attributed SDD, and another one is L attributed SDD. So what is S attributed SDD? S attributed SDDs are basically SDDs with all the attributes, with all attributes are synthesized. So all the attributes are synthesized attributes. Okay, we already know what are synthesized attributes and what are inherited attributes, right? But L attributed SDDs are basically attributes can be synthesized plus the attribute can be inherited. So some attribute can be synthesized and some attribute can be inherited attribute, right? But there is a condition for inheritance. So if your attribute is inherited, it should always be, it should always inherit from itself. It should always inherit from itself, or it can inherit from its parent, and it can inherit from its sibling, right? But the sibling must be left sibling, right? So your L attributed SDDs is basically a SDD with attributes that can either be synthesized attribute or they can be inherited attributes. And if they are inherited attributes, it can only inherit from itself, right? It can only inherit from itself, or it can inherit from its parent, or it can inherit from its sibling. If it inherits from the sibling, it always should inherit from left sibling. It cannot inherit from the middle sibling or the right sibling. Okay, it should always inherit from the left sibling. It cannot inherit from the right sibling. Okay, so that is why it is known as L attributed, because it is inherited plus synthesized, but the inheritance is only for left children. So let's look at an example. Suppose uh, okay, so suppose all this let's draw some more. So suppose this is your pass tree. So suppose all of these node are basically your non-terminal, right? And this has some attributes. So suppose all of them has a attribute called v. So there is a dot v, a dot v, and again there is b dot v. Okay, so all these are attributes. Now suppose the value of b dot v is being calculated like this: e dot v plus uh, b dot v. Okay, so here this v attribute, so this is an attribute, right? Is this a synthesized attribute or inherited attribute? So this is a synthesized attribute because it is calculating value by taking the value from itself or by taking the value from its children, right? It is not taking any value from its parent or its sibling. Okay, now uh, let's say the value of c is being calculated like this: c dot value, whatever the value c dot value has, plus f dot value. Okay, again, is this v uh, synthesized or inherited attribute? Synthesized, right? But if you add a semantic rule that says it is taking value from uh, d dot v. Now is this uh, c dot v, the attribute v, is it synthesized or inherited? It is inherited because it is taking the value from the right sibling. So d is the right sibling of c and b is the left sibling of c. Okay, so it is taking the value from the right sibling. So can we say, if we have this information so far, can we say these semantic rules are, or this SDD are uh, L attributed STD. Can we say that? Is it a L attributed STD? Why not? Because it is calculating one of its attribute with the value of its right side sibling, which is D, and that is not allowed in L attributed STD. But if this was sorry, but if this was uh, B dot V, we can call it as L attributed SDD, right? Because it is calculating the value from left sibling. It is an inherited attribute, that is fine, but the inheritance is limited towards the left sibling. Okay, and if it was inherited attribute, it would not calculate any value from its children. So it would be simply like this. Okay, so this is basically your S attributed STD and your L attributed STD. Okay, so this is your dependency graph, and here your S attributed SDD and L attributed STD. So what does it say? An STD is S attributed if every attribute is synthesized. So that means all of the attribute must be synthesized. So if we look at this example, this SDD is an S attributed SDD because all of the attributes here are synthesized attribute. Clear? There is no inherited attribute here, so this can be S attributed STD. If you look at L attributed STD, the attributes can either be synthesized or it can be inherited. Meaning the attribute can be synthesized or it can be inherited. If it is inherited, it must follow some rules. That inheritance should always be from the left children. It can inherit from itself, it can inherit from its parent, or it must inherit from the left sibling. It cannot inherit from any value from right sibling. It always should be left sibling. Okay. So this is basically S attributed SDD and L attributed SDD. Now let's look at an example for inherited attribute. Let's see. So you might be asked to draw a annotated pass tree for the string 3 multiplied by 5, right? So first what you need to do, first you need to use this grammar. You need to use this grammar to draw a parse tree that will generate 3 into 5, and in that parse tree you need to provide all the attributes, right? And you need to calculate those attributes, right? So this is basically attributes that have inheritance. So if you can see in the semantic rules, so this is basically your four rules and the corresponding semantic rules associated with it. So one production rule can have multiple semantic rules. Suppose here is one semantic rule and here is another semantic rule. So far you have seen only one semantic rule for one production, right? But one production can have many semantic rules. So our first two production has two semantic rules associated with it, and the last two has only one semantic rule associated with it. This SYN attribute is a synthesized attribute. This VAL attribute is a synthesized attribute. Okay, and this INH is inherited attribute. Lexical value is always synthesized attribute, right? Because this is not, uh, it is not being calculated, but it is directly fetching from the symbol table where the values are set. So lexical value is basically your synthesized attribute. So SYN is your synthesized attribute. This VAL is your synthesized attribute. The only inherited attribute is INH. Okay. Now you are given this information and you are asked to draw the annotated pass tree for this 3 into 5. So to do this, let's wait. Okay, so to do this, you will first draw the uh, first draw the parse tree that will generate 3 into 5. So if you start from, okay, so if you start from the start symbol, so we can start from T, right? And we can use this production. T produces F T prime. So F and T prime, right? And after that, we need to generate 3 into 5, right? So this F will be derived from 3. So the F will be digit. So we can use this rule. So F can be digit, right? And this T can be this rule. The T can be expanded into this rule. So the T prime can be expanded into this rule, which is multiplication F T prime. So multiplication multiplication F T prime. So far we have, this digit will be 3. So far we have 3 multiplication and we need 5, right? So this F can produce digit, right? And this digit can produce 5. So now we have 3 multiplication 5 and this T. But this T can be easily converted into epsilon using this rule. So T produces epsilon. So here we have generated 3 into 5 from this grammar using the parse tree, right? So this is your parse tree. And now you are going to convert this parse tree. Look carefully. You are going to convert this parse tree you are going to convert this pass tree into annotated pass tree by writing t dot val here, because this t has one attribute, which is synthesized attribute, which is value. Okay. Now for this f also has one synthesized attribute, which is value. Digit also have one attribute, which is lex value, right? Okay. Now for this t prime, if you look closely, this t prime has two attributes. One is inherited attribute, one is synthesized attribute. So you need to write it two times. So this t, for this t prime, you need to write it two times. One for inherited, one for synthesized. Okay. Similarly for f, only one. Similarly for this digit, only one. But for this t prime again, it again has two attributes. One is inherited, one is synthesized. So we need to write it two times. Is it clear how you can uh, draw this annotated parse tree for this string? Okay, 3 into 5. Is it clear? T val is only for the terminal, non-terminal t, right? We also have another non-terminal, which is t prime. Those are different. Okay, t is one non-terminal and t prime is another non-terminal. For t, if you look at the semantic rules, we only have one attribute, which is value. But for t prime, we have two attributes, which is inherit here, and if you look here, we have another one, which is synthesized. Is this part clear? এবার বুঝছেন পুরোটা না কনফিউশন আছে? Okay. Any more questions? Okay. So now that we have this, we're going to simply construct or evaluate, right? So for dependency graph, we need to make these lines dotted, right? We need to dash these lines. So I'm not doing it fully. I'm just gonna calculate the value. So first of all, here we're going to get 3, right? From digit dot lex value. So we are going to get 3 from digit dot lex value. I'm writing this value here. And we are going to get 5 from here, digit dot lex value. Now this 3 will be passed to f, because f dot value is digit dot lex value. So this here will be passed to f, which is 3. Okay. Again, here the 5 will be passed to f. Now if we look at here, t produces ft prime. So t produces f t prime. We can see that t1 dot inherit is equal to f dot val. What is the f dot val? F dot val is 3. So t1 is inheriting the value from f dot val. So it is inheriting the value from left sibling. What is the value? The value is 3. So the inherit value of t prime is 3. So the inherit value of t prime is 3. Now, what is the synthesized value? The value of t val, the value of t val is equal to t prime dot synthesize, t prime dot synthesize. But we do not have any synthesized value at the moment. So this is blank. So this will be blank as well. But if you look at this production rule, t produces multiplication f t prime, then it says t one dot t1 prime dot inherit, meaning this is basically t prime inherit. So it is taking the value from here, right, and multiplying it with f dot value. So multiplying it with f dot value, this f dot value, right? So it is taking 3 and 5, 3 from t prime inherit, and it is taking f from 5 from f dot value. So it is getting 50. right? So it is taking this value from parent, this 3 from its parent, and this 5 from its sibling. So it is getting 50. So what is the synthesized value of t? The synthesized value of t prime, the value of t prime, this synthesized value is equal to this synthesized value, but this synthesized value is empty. It is not calculated yet, right? So it is going to be calculated from this rule. So T produces epsilon. So T prime produces epsilon. The value of T prime synthesized is T prime inherit. So the value from T prime synthesized will come from the value from T prime inherit, T1 prime inherit, which is 50. Right? So it is taking the value from itself. Now this synthesized value will go here, the 15 will go here, and this synthesized value will go here, right? So this is basically your dependency graph of this evaluation. So we have evaluated 3 into 5, which is equal to 15, by using this grammar. Any confusions, any questions? So if you noticed here, we are not following any depth first traversal, right? Because we can, this has a inherited attribute. So we are just saying which one should we calculate first to get the benefit, right? So we are just using our eyes to calculate this. Some computer, some compiler might have some conditional based algorithm to which node to calculate first for these types of inherited attributes, right? But we cannot simply use any type of depth first search traversal to compute this, just like we did in synthesized attribute. It is not possible because it has some inherited attribute. But the compiler can have some conditional based algorithm that can check if this is a string, I should calculate this node first, right? So doing this, the compiler can evaluate it. Okay, any questions from this part? So you might be asked how to draw the dependency graph of 3 into 3 into 3, right? That is also able to generate from this SDD, right? So you need to practice this at home. Okay, any questions? Okay, that was basically your lecture 11. So we finished lecture 10 yesterday. This is lecture 11. Now we have another half an hour remaining. So what we are basically gonna do is we're going to look at lecture 9. Uh, should be lecture 9. Let me see. Wait. Uh, not this. Right. So we had lecture 9 before mid, and I'm going to quickly review this lecture. Okay, because you have already done it in your previous class, right? You also should have notes regarding this. I have shown the simulation in class at least 2 times. Okay, now I'm going to show the simulation again. And before this, any questions from today's top lecture? Eh, yes, রাইট। প্রত্যেকটা ক্লাসই অনলাইন হবে এখন। আমার এখনো ১.৫ মাসের মতো বেড রেস্টে থাকতে বলছে। ওকে, সো এনি কোশ্চেন রিগার্ডিং টু দিস ক্লাস? Sure, sure. If you have any questions, mail me for a consultation hour as well. Okay. Okay. Let's start. So you will be given uh, a parsing table, right? So this is your parsing table. So you will be given a parsing table, right? Like this, and you will be also given a grammar like this, right? It will be numbered as well. So this is one, this is two, this is three, this is four, this is five, this is six. So all those rules will be numbered as well, and you will be given a complete parsing table, right? So this is your complete parsing table, and you will be asked to check if a certain string is parsable by this table or not. Okay, so let's look at the table. What are, yes, no, you will be given the parsing table. Okay, so let's see what is the parsing table. The parsing table will have different states. These states are the states in your automata, right? So from a grammar, you found out the uh, canonical item set of LR0, and you have constructed the automaton, right? So those automaton had states. If you remember, those automaton had states. So these are the states of your automaton, and this should be in your parsing table. And parsing table will have few columns. It will mainly have two types of columns. One is the action column containing multiple action values, and one is a go to column containing multiple go to values. So if you can see, the action column is only for the non terminals, sorry, only for the terminals. Here id is a terminal, plus is a terminal, multiplication is a terminal, then opening bracket is a terminal, closing bracket is a terminal. If you look at this grammar, you can see what are those terminals. These terminals will be in actions column. With addition to this, one more column will be added into the actions column, which is the dollar sign. So dollar signs are basically used to understand the end of a string. Suppose this is your string, A, B, C, D, E, F, G. So suppose this is a string you need to parse, and to indicate the end of the string, you need to add a dollar sign at the end, right? So this is another action for a dollar sign. And your go-to columns, you will have all the term all the non-terminals. So here E is a non-terminal, T is a non-terminal, F is a non-terminal. If you look at this grammar, you can see E, T, and F are the non-terminal. And what are the terminals? Your ID is a terminal, right? ID is a terminal. This is opening bracket is a terminal, closing bracket is a terminal, multiplication is a terminal, plus is a terminal. And for every parsing table, dollar will be added as a terminal by default, right? So actions have two types of actions. One is a shift option, which is represented by S, and another is reduce action, which is represented by R. And sorry, there are four types of action. One is shift, one is reduce, one is accept, and one is error, right? So shift operations will be marked by S, and reduce operations will be marked by R. The accept operation will be marked by ACC, which means accept, and the error operations will be blanked. So this cell, this cell, this cell, all the blank cells are error operations. Okay. Similarly, the go-to columns will have only numbers. There will be no shift operation, no reduce operation, no accept operations. It will have only numbers, meaning it will go to state number 1, this will go to state number 2, this will go to state number 3. Similarly for all this. Okay. Any questions from the uh, parsing table? Any questions? Okay. So you will be given this table, you will be given this grammar with numbered production rules, and you will be asked to uh, suppose you will be asked to evaluate. So you will be asked to evaluate if this input is parsable by this parse table order, right? So you'll be asked to evaluate if this input is parsable by this parse table order. Okay. So what you need to do, you need to create a table like this. So one will have a stack, another one is symbol, another one is input, and another one is action. So uh, you create this table and put the, this is not a table basically. uh, this is the simulation part. You do not necessarily need to give rows and columns like a table. You can write it under one another, that is also fine, but it should have four columns. One is stack, one is symbols, one is input, and one is action. Your input is the input given in your question that you need to verify, and after that you need to add a dollar sign. So your first task is to add a dollar sign in with the input and put it under the input field. Okay. Now after this, your stack and symbols are basically your, they are both stacks. So you can imagine the stack like this. It is a vertical stack. So uh, you have seen the stack representation like this, right? We are simply rotating it and making it like this. So this is the bottom of the stack, and this is the top of the stack. Okay. So in your stack, the first state 0 should be here. So your stack should have a state 0 because this is your starting state of the table. So the starting state of the table should be at the top of the stack. Okay. So if you consider this as stack, right? So this is basically the top of the stack. It should have 0. Okay. Now you need to look for action. What action should you perform? Suppose the top of the stack is 0 and your input, top of the input is id. So you need to go to the 0th row of the state and look for the column id. So you have the action S5, that means shift 5. So your action is shift 5. So your action is shift 5, right? So you're going to shift 5 into the stack, right? And also you are going to shift this input into the symbols as well. Okay. Again, the uh, bottom of the symbol, the symbols is also an stack. So bottom of the symbol stack will hold a dollar sign. Okay, so the bottom of the symbol stack will hold a dollar sign. So you need to add a dollar here. This is to indicate if it is the end of the stack or not. Okay, now as the operation is shift 5, that means you need to take this input, which is id, and shift it to the symbols, and you also need to shift the state 5 into the stack. So your stack will be 05, your stack will be 05, your symbol will be dollar id, okay, and your input will be plus id into id dollar, right? Because this id, because this id is shifted here, and also the state is shifted on top of the stack as well. So if you imagine this as a stack, on the top of the stack you have 5. Before you had 0, now you have 5. Okay, now what is in the top of the stack? In the top of the stack we have 5. And what is the input? Current input, our current input is plus, right? This is our current input string. So what we need to do, we need to go to state 5 and look for the plus symbol. So this is the plus symbol. So our operation is reduction, R6. So we need to say our action is reduce by rule 6. But what is rule 6? Rule 6 is basically F produces ID. So reduce by F produces ID. Okay. So this is our action. For next step, our action is reduce by F produces ID. So whenever you are reducing, you need to do two things, right? First of all, you need to calculate the cardinality of this production rule. So to calculate the cardinality, we are going to simply calculate how many terminals or non-terminals are in the production body part. So how many terminals are non-terminals in this production, in the production body? Only one, right? For this, uh, sorry, for this, how many? Uh, can you speak again? Right, right. Okay. So for this, one, two, three, right? So the cardinality of this production is 3. What about this production 4? What is the cardinality? 1. Okay. So for production 3, what is the cardinality? So T1, this multiplication 2 and this F3. So 3. For production 2, 1. So for production 1, the cardinality is 3, right? So we need to calculate the cardinality of the rule that is being reduced by. So in our case, this is F produces ID and the cardinality is 1. If the cardinality is 1, we need to remove one value from the stack, one value from the top of the stack. If the cardinality is 2, we need to remove two values from the top of the stack, right? But before that, this is being reduced, right? This id is being reduced, right? So this id is being reduced. It is being reduced by what? It is being reduced by this f, right? So we need to write f. So here, as this id is being reduced, we need to write f here because this is being reduced. Okay, that is fine. Now, as I said, what is the cardinality of this? 1. So we need to remove one value from the top of the stack. If this was 2, we need to remove two values from the top of the stack. If it was 3, we need to remove three values from the top of the stack. So as this is uh, 1, we remove 5 as it is in the top of the stack. So in our stack, 0 will be there. We remove 5. Okay. So what was the first part? We calculated the cardinality, we reduced the symbol, and we removed one value from the top of the stack, or the number of cardinality from the top of the stack. This is part 1. Okay. Now we need to do part 2. For reduced operation, what is the part 2? For part 2, we need to check what is the current top of the stack. What is the current top of the stack? 0, right? Okay, so what is the current top symbol? F, right? So we need to go to 0 and we need to go to F column. So what is the value? We have 3. So our stack value will, so we need to push 3 into the top of the stack, because after reduce operation we need to perform one go to operation. So after we did reduction, the current top of the stack was 3 and the current top symbol was F, so we need to go to 0 F and we get go to 3, so we need to push 3 into top of the stack. Okay. Okay. So did our input changed after this operation? Did your input changed? Okay, so the input remains the same, right? So similarly, again, you will repeat this until you get accept, right? So similarly, you are going to repeat this process until you get this accept, or until you hit any of the blank uh, uh, cell which is error, right? Or if your stack is empty, so these will cause errors, right? Or you can accept. If you hit accept, that means your string is parsable by this parse step. So let's quickly complete this. Uh, so this 3 and the top of the 3 and plus. So the top, the current input is plus. So you go to 3 and plus. We do R4, right? So we do R4. To reduce this F will be reduced into T. So the cardinality is 1. So the 3 will be removed. The 3 will be removed from the top, and we need to go to 0 of t. So 0 of t is 2. So we need to push 2 here. So this 2 is being pushed here. And our input remains the same. So whatever the input is plus id in into id dollar remains the same. Okay. So what is the current action? The current top of the stack is 2 and the current input is plus. So we go to 2 and plus, this is R2. So here we have reduce by rule, sorry, reduce by rule 2. What is rule 2? E E produces T, right? So this T will be reduced into E, and the cardinality of this is 1, so 2 will be removed from the stack. In our stack we have 0. Now we need to see 0 of E. What is the 0 of E? It is go to 1. So we need to push 1 on top of the stack. Also, our input did not change. So our input will remain the same, which is plus ID into ID dollar. So what is the current action? The current action is we need to see what is the top of the stack. 1. What is the top of the input? That is 0, right? So for 1, sorry, that is plus. For 1 and plus, we do shift 6. So that means 6 will be shifted into the stack. Okay, our symbols will also get a new shift, which is dollar, sorry, uh, dollar E, then plus, right? Our input will now change because this plus is shifted here. Our input will become ID into ID dollar, right? Okay. So what is our next action? Our next action, top of the stack is 6. Top input is ID. So we go to state number 6 and we go to ID cell. It is shift 5. So our next action is shift 5. So we shift 5. So 0165, right? So our input will also change. We need to shift ID here. Our input will be multiplication ID, right? So what is the current operation? In the top of the stack we have 5, and input, top of the input is plus. So we go to state number 5, and for plus, sorry, for star, what do we have? For star we have R6. So reduce by F produces ID. হ্যাঁ বলেন। পারবেন না। ওখানে লিখবেন যে কনফ্লিক্ট ইন দ্য অ্যাকশন টেবল ক্যান নট পার্স ফার্দার। Okay, so what should be the current action? We need to reduce, right? So if you reduce, what is the cardinality? Cardinality is 1. So 0, 1, 6, 5 will be removed from the stack. Our symbol will be reduced, which is dollar E plus this ID will be reduced to F. Our input will not change. Our input will remain the same, ID dollar, right? So what should be our go to? We are not done yet. We need to compute the go to. So we need to go to the state 6 and we need to see the go to of F. So go to of F. So for state 6, the go to of F is 3. So we need to push 3 into the stack. So we need to push 3 into our stack. Okay. Now, what should be the action? On the top of the stack, we have 3, and our input is star, right? So, uh, our action is reduced by rule 4. So, what is the rule for T into F? So, reduce by rule 4. Similarly, you will do all this, and at some point, you will find this action, which is accept. So in actions, you will write accepted, and you will complete the parser, right? So also, your book has an example as well. Right, so there is an example which is id into id plus id. This is another example. It's in your book as well, in page 253, right? So you should practice this, or you can try with this string. So suppose you are given, or suppose you are given this string, right? So bracket id into id plus id, bracket close, multiplication, bracket open, id plus id, bracket close, right? So you might be given this long string, and you are asked to verify it is possible to parse this string or not using this parsing table, right? So you can be given a small string, you can be given a long string. So you need to practice this in your home. Okay. Any questions? Okay, so that's it for today's class. If anyone have any questions, please feel free to ask. Anyone have any questions? Okay, I'm closing the recording.